Welcome to Cosmos and Dreams. Tonight, we explore a star that shouldn't exist, older than time itself, an ancient light burning quietly against everything science thought it understood about the universe. If the universe is your kind of bedtime story, subscribe before you drift off. Now get comfortable, close your eyes, and let science carry you to sleep. Opening meditation. Close your eyes for a moment. Imagine you are standing outside on a clear night. The air is cool. The ground beneath you is solid and still. Above you, the sky opens up in every direction, a deep, quiet black, scattered with points of light so ancient that the light reaching your eyes left its source before your great-grandparents were born. Before their great-grandparents were born. Before any human being walked the surface of this earth. And somewhere in that darkness, not visible to the naked eye, but there, nonetheless, there is a single star. A small, faint, unassuming point of light in the constellation Libra. You might look right past it on any ordinary night. But this star holds a secret so strange, so quietly unsettling, that when astronomers finally understood what they were looking at, they stopped in their tracks. Because according to the numbers, according to the best measurements that human science could produce, this star appeared to be older than the universe itself. Older than everything. That should not be possible. And yet, there it was. A small, ancient light in the sky, patiently waiting for us to understand it. Tonight, we are going to follow that mystery, gently, slowly, through centuries of human curiosity and discovery, from the first people who looked up at the stars and tried to name them, all the way to the scientists who found themselves staring at a number that could not be true, and what happened when they tried to figure out why. Let your body settle. Let your breath slow. The stars are not going anywhere tonight. Part 1: A light in the wrong time. What does it mean for something to be older than everything? That question sounds almost like a riddle. Something you might find written on a card at the end of a long table in a dream. And yet for a period of years in the late 20th century and into the early 21st, it was not a riddle at all. It was a genuine scientific problem, documented, published, debated in journals and conference rooms, and quietly kept alive by a small number of astronomers who refused to let it go. The star in question is catalogued under the name HD 140283. It is located approximately 190 light-years from Earth, which in cosmic terms is almost laughably close, a neighbor, in stellar geography. It sits in the direction of the constellation Libra, the scales. And it has been visible to telescopes for well over a century. In that sense, it is not a new discovery at all. What is new, or rather, what became increasingly precise and increasingly troubling over decades of refinement, is the estimate of how old it is. For much of the 20th century, astronomers had a rough sense that HD 140283 was very old. The composition of its atmosphere, the mix of elements detectable in its light, told a clear story. It was what astronomers call a metal-poor star. In astronomical language, metals refers to any element heavier than hydrogen and helium. And HD 140283 had almost none. That matters enormously. Because heavier elements, iron, carbon, oxygen, calcium, are not produced in the Big Bang. They are made inside stars, over millions and billions of years of nuclear fusion, and then scattered into space when those stars explode. The universe begins with almost only hydrogen and helium. Everything heavier comes later. So a star with almost no heavy elements is a star that was born very early, before the universe had time to build much of anything beyond its original ingredients. It is like finding a house with no furniture, no plumbing, and no electricity, and concluding that it must have been built before modern conveniences existed. The simplicity itself is the evidence. HD 140283 is sometimes called the Methuselah star, after the biblical patriarch said to have lived for 969 years. The name was given informally, by astronomers who recognized what they were dealing with, something almost impossibly ancient. A survivor from the earliest chapter of the universe's story. The question was, exactly how old? Measuring the age of a star is not a simple task. You cannot look at a star and read a date. You cannot drill a core sample, the way geologists do with ancient ice or rock. What you can do, what astronomers do, is study the star's light with extreme precision, modeling its internal physics, and compare it against the mathematical predictions of stellar evolution. Stars, like all physical systems, change over time in predictable ways. They are born from collapsing clouds of gas and dust. They spend most of their existence fusing hydrogen into helium in their cores, the process that makes them shine. Eventually, they exhaust that hydrogen, and their structure changes. They swell into red giants, or, depending on their mass, they collapse, or explode, or quietly dim to embers. By studying where a star sits along the evolutionary path, what temperature it is, how bright it is, what its surface composition looks like, astronomers can work backward and estimate when it was born. It is a technique called stellar isochrone fitting, and it has been refined over many decades. When astronomers applied this technique to HD 140283 with careful measurements, the numbers they kept getting were striking. The star appeared to be somewhere between 14 and 16 billion years old. The estimates varied depending on assumptions, on which models were used, on the precision of the measurements. But the central figure, roughly 14 to 16 billion years, kept appearing. And the age of the universe? According to the best measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, the universe is approximately 13.8 billion years old. Which means that HD 140283, according to those early estimates, appeared to have formed roughly 1 to 2 billion years before the universe existed. Which is, of course, impossible. A star cannot be older than the universe from which it emerged. It cannot have formed before the atoms from which it is made existed. The laws of physics do not permit this. And yet, there was the data. The astronomers who studied this star were not careless. They were not fools. They were careful, methodical scientists, working with the best instruments available, checking and rechecking their numbers. And they kept arriving at the same impossible conclusion. What followed was one of the most fascinating quiet dramas in modern astronomy, a decades-long effort to understand how both measurements could be right, and what the answer might reveal not just about one ancient star, but about the nature of the universe itself. There is something quietly profound about this puzzle. It is not a story about destruction or catastrophe. It is not a mystery wrapped in darkness. It is a story about precision, about how deeply our understanding of the cosmos depends on measurement, and how even small errors, carefully buried in our best equations, can produce contradictions that sound like the universe is breaking its own rules. It is a story about what happens when science takes itself seriously enough to sit with an impossible number and say, "We do not understand this yet. But we will." Part 2: The Birth of Stellar Archaeology. How do we know how old a star is when we cannot touch it? That question is worth sitting with for a moment. It seems almost naive, and yet it is genuinely one of the deepest challenges in observational astronomy. We are separated from even the nearest stars by distances that no human instrument has ever crossed. We receive from them only light, ancient, faint, traveling across unimaginable distances to fall on our instruments and our eyes. But light, it turns out, carries an extraordinary amount of information. Far more than our ancestors could have imagined. The story of stellar archaeology begins in the early 19th century, in a small workshop in Munich, Germany, where a young man named Joseph von Fraunhofer was doing careful, systematic work with a prism and a narrow slit of sunlight. Fraunhofer was a craftsman of exceptional skill, a lens maker, a scientific instrument builder, who had taught himself optics through long years of practice in a workshop where conditions were often difficult. His early life had been hard. He had been orphaned young and placed in an apprenticeship that was more servitude than education. But he had a gift for precision, and he applied it to everything he touched. In 1814, Fraunhofer began a systematic examination of sunlight spread through a prism into its component colors. What he saw, when he looked closely, was not a simple smooth rainbow. The spectrum of sunlight was crossed by dark lines, hundreds of them, thin and precise, at specific wavelengths of color. Where the rainbow should have been smooth and continuous, there were absences. Gaps. Some of these dark lines had been noticed before. The English chemist William Hyde Wollaston had glimpsed a few of them in 1802. But Fraunhofer mapped them systematically. He catalogued over 500 of them, assigning letters to the most prominent, the D lines in the yellow, the C and F lines in the red and blue, and so on. These became known as Fraunhofer lines, and they transformed the study of light. At the time, no one fully understood what caused them. That understanding came later, from the work of Gustav Kirchhoff and Robert Bunsen in the 1850s. They discovered that each chemical element, when heated, emits light at specific wavelengths, its own unique fingerprint of colors. And conversely, when a cooler gas of that element is placed in front of a bright continuous light source, it absorbs light at exactly those same wavelengths, creating dark lines. The Fraunhofer lines in sunlight, they realized, were absorption lines, produced by cooler gases in the outer atmosphere of the sun absorbing specific wavelengths from the brilliant continuous light of the deeper interior. And since each element has its own unique set of wavelengths, you could read the chemical composition of the sun directly from its spectrum. This was an astonishing discovery. It meant that we could analyze the chemistry of the sun, and of every other star, simply by spreading their light through a prism. The universe had suddenly become legible. Kirchhoff famously declared that spectral analysis would allow us to examine the composition of stars that no human being would ever visit. He was completely right. This technique, spectroscopy, became the foundation of modern astrophysics. It is the reason we know anything at all about the composition of HD 140283, or any other distant star. The development of spectroscopy through the second half of the 19th century was rapid and extraordinary. Astronomers began attaching spectroscopes to their telescopes and cataloging the spectral lines of star after star. They found that different stars had different spectra, different mixes of absorption lines, indicating different surface temperatures and different chemical compositions. One of the most significant contributions came from the work carried out at Harvard College Observatory in the late 19th and early 20th centuries, through a project that would eventually be called the Henry Draper Catalog, HD for short. That is where the HD in HD 140283 comes from. Henry Draper was an amateur astronomer and physician who made significant contributions to stellar spectroscopy before his death in 1882. His widow, Anna Draper, funded a major program at Harvard to classify the spectra of hundreds of thousands of stars in his memory. The work was done largely by a team of women, who were called human computers in the language of the time, as they performed vast amounts of mathematical and analytical work that would today be done by machines. Their contributions were essential and for a long time under-recognized. Among them was Annie Jump Cannon, who devised the stellar classification system that we still use today. Cannon could classify 3 stars per minute by eye, an extraordinary feat of trained perception, and over her career she classified nearly 500,000 stars. She arranged stars into spectral classes based on their temperature, from the hot blue O-type stars down through B, A, F, G, K, and M to the cooler red dwarf stars. Another member of that team was Cecilia Payne, later Cecilia Payne-Gaposchkin, who in 1925 made a discovery that was initially rejected and then gradually recognized as one of the most important findings in the history of astrophysics. She demonstrated, through careful analysis of stellar spectra, that the Sun and stars are composed overwhelmingly of hydrogen, that hydrogen is by far the most abundant element in the universe. Her doctoral supervisor, Henry Norris Russell, initially told her she must be wrong and convinced her to downplay the finding. He later reached the same conclusion independently and received much of the credit. Payne-Gaposchkin's priority has since been widely acknowledged. Her discovery matters deeply to the story of the Methuselah star, because it established the baseline: the universe begins predominantly hydrogen and helium. Everything else, every heavier element, comes later, through the nuclear furnaces inside stars. A star born very early would contain almost nothing heavier than helium. And HD 140283 contains almost nothing heavier than helium. That is the first evidence, the deepest evidence, of its age. But reading the composition of a star from its light is only the first step. The second step, calculating its age, requires a completely different branch of physics. It requires understanding how stars are born, how they live, and how they die. And that understanding took most of the 20th century to develop fully. The fundamental physics of stellar energy was not understood until the 1930s. Before that, the question of what powered the sun was genuinely open. Some scientists had proposed chemical reactions, but chemical reactions could not produce enough energy to keep the sun burning for more than a few thousand years, far too short a time to explain the geological record of life on Earth. Others proposed gravitational contraction, the Kelvin-Helmholtz mechanism, which could sustain the sun for tens of millions of years, but still not long enough. It was the development of quantum mechanics and nuclear physics in the 1920s and 1930s that finally provided the answer. In 1938, the German-American physicist Hans Bethe published a landmark paper describing the proton-proton chain, the set of nuclear fusion reactions by which hydrogen nuclei combine to form helium, releasing enormous amounts of energy in the process. This was the power source of the sun. And at a stroke, it explained everything: the sun's luminosity, its long lifespan, the fact that the Earth had been warm for billions of years. Bette's work, combined with the discoveries of Pangaposhkin and the spectral catalogues of Cannon and her colleagues, laid the groundwork for what would become stellar astrophysics, the science of understanding how stars evolve over time, and therefore how old they are. Part 3: The Hertzsprung-Russell diagram and the clock in the sky. Is there a clock hidden in the pattern of the stars? Early in the 20th century, two astronomers working independently on different continents made the same strange discovery. When they plotted the brightness of stars against their color, their temperature, a remarkable pattern emerged. The stars did not scatter randomly across the graph. They arranged themselves into a clear structure, like a map with roads and districts and zones. Edgar Hertzsprung was a Danish astronomer, working in the early 1900s, who had noticed that when he compared the colors of stars to their absolute luminosities, correcting for distance, certain groupings appeared. Henry Norris Russell, at Princeton, reached similar conclusions around the same time, and published an influential version of the diagram in 1913. The diagram that bears their names, the Hertzsprung-Russell diagram, or HR diagram, became one of the most important tools in all of astrophysics. It is, in a sense, a map of stellar life. Most stars, when plotted on this diagram, fall along a diagonal band running from the upper left, hot, bright blue stars, to the lower right, cool, dim red stars. This band is called the main sequence. Our sun sits comfortably in the middle of it, a medium temperature, medium brightness yellow-white star classified as spectral type G. Stars spend most of their lifetimes on the main sequence. This is the long, stable phase of their existence, when they are burning hydrogen in their cores through nuclear fusion. The more massive a star, the hotter and brighter it burns, and the faster it consumes its fuel. The most massive blue stars at the top of the main sequence last only a few million years. The dimmest red dwarf stars at the bottom may continue burning for trillions of years, far longer than the current age of the universe. When a star exhausts the hydrogen in its core, it changes. It evolves off the main sequence, typically expanding and cooling to become a red giant, or, depending on its mass, a red supergiant. In the HR diagram, it moves to the right and upward from its main sequence position. Eventually, it ends its life through one of several possible pathways: a quiet shedding of its outer layers to form a planetary nebula, a violent explosion as a supernova, or, for the most massive stars, a collapse into a neutron star or black hole. The critical insight, for understanding stellar ages, is this: different stars spend different amounts of time on the main sequence, and those times are governed by physics that we can calculate with considerable precision. For a group of stars all born at the same time, a star cluster, the HR diagram becomes a direct clock. When the cluster is young, all its stars sit on the main sequence. As time passes, the most massive, hottest stars at the upper left evolve off the main sequence first. Then, over billions of years, progressively less massive stars follow them. The point where the cluster's stars begin to peel away from the main sequence, called the main sequence turnoff point, moves progressively downward and to the right as the cluster ages. By measuring where the turnoff point is for a given cluster, or for a given old star, astronomers can read off its age. It is like reading a thermometer, but instead of temperature you are reading time. This technique, known as isochrone fitting, is how the age of HD 140283 has been estimated. Astronomers measure the star's temperature, its luminosity, its surface gravity, and its composition, and they compare these measurements to mathematical models of stellar evolution. The models say, a star with these characteristics, with this composition, burning its fuel at this rate, would reach this point in its evolution after approximately this many billions of years. The models are not perfect. They depend on assumptions about the internal physics of stars, about how energy moves from the core to the surface, about the precise nuclear reaction rates involved, about whether and how much mixing occurs between different layers of the stellar interior. Each of these assumptions introduces small uncertainties. And in the case of HD 140283, those small uncertainties matter enormously, because the difference between a star that is 13 billion years old and one that is 16 billion years old, the difference between consistent with the universe's age and impossibly older, is not enormous in absolute terms. It is a few billion years in 14 to 16 billion. It falls within the range of uncertainty in the models. That is the heart of the mystery. Not that the star is definitively older than the universe, but that it appeared, within the error bars of measurement, that it might be. And that appearance demanded explanation. To understand how that explanation was pursued, we need to go back a step further, to understand how the age of the universe itself is measured, and how uncertain that measurement has been. Because both sides of the paradox, the age of the star and the age of the universe, rest on measurements made with instruments of imperfect precision, and interpreted through models of imperfect completeness. The mystery of the Methuselah star is not just a story about one ancient sun. It is a story about the limits of human knowledge, and the extraordinary effort required to push those limits even slightly further. In the cool, quiet darkness of space, the star has been burning for longer than we can quite comprehend. It does not know that we have found it puzzling. It does not know that its existence caused long hours of careful work in observatories and laboratories around the world. It simply burns, slowly, steadily, red, orange and old, waiting with perfect patience for us to understand what it is telling us. Part 4: Measuring the Age of Everything. What is the age of the universe, and how do we know? It is one of the oldest questions of human thought. How long has the world existed? And for most of human history, the answers came not from physics or mathematics, but from myth, religion, and philosophy. The ancient Hebrews, calculating from the genealogies in Scripture, arrived at an age of the world of a few thousand years. The ancient Hindus arrived at numbers that were, in their own way, closer to the truth, vast cycles of time called kalpas and yugas, stretching over billions of years. The geological evidence for a very old Earth began to accumulate seriously in the 18th and 19th centuries, as naturalists and geologists, James Hutton, Charles Lyell, and eventually Charles Darwin, recognized that the deep rock record required enormous timescales to explain. But the precise quantification of those timescales, the actual numbers, came with the development of radiometric dating in the early 20th century. The age of the universe itself, as a scientific question with a scientific answer, is a product of the 20th century's revolution in cosmology. It begins with the discovery, in the 1920s, that the universe is expanding. Edwin Hubble is the name most associated with that discovery. Working at the Mount Wilson Observatory in California, using the largest telescope in the world at the time, Hubble in 1929 published observations showing that distant galaxies are receding from us at speeds proportional to their distances. The farther away a galaxy is, the faster it moves away. This is now known as Hubble's law, and the constant of proportionality, the ratio of recession speed to distance, is called the Hubble constant, denoted h. The implication of this expansion is profound and, once understood, almost obvious. If everything is moving apart from everything else now, then at some point in the past everything was compressed together. Run the expansion backward in time, like a film in reverse, and the universe converges on a single point, an infinitely dense, infinitely hot beginning. The Big Bang. The age of the universe is related to the Hubble constant in a simple way. The inverse of h, 1 divided by the Hubble constant, gives an estimate of the time since the expansion began, roughly speaking. So if you know h, you can calculate the approximate age of the universe. When early estimates of the Hubble constant pointed toward a younger universe, 10 to 12 billion years, the problem with HD 140283 was not just a matter of the star's precise age. The star seemed to be potentially 2 to 4 billion years older than everything. That was a serious problem. It could not be dismissed as measurement noise. The resolution began to come, slowly, in the 1990s and 2000s, through several converging lines of evidence. The first was the Hubble Space Telescope Key project on the extragalactic distance scale. One of the primary scientific justifications for building the Hubble Space Telescope, launched in 1990, was to measure the distances to galaxies accurately enough to pin down the Hubble constant. For 8 years, a team of astronomers led by Wendy Friedman used the telescope to measure distances to dozens of galaxies using a type of variable star called a Cepheid, a star that pulsates in brightness with a period directly related to its luminosity, making it a reliable distance indicator. In 2001, Friedman's team published their result, h equals 72 plus or minus 8 kilometers per second per mpc, kilometers per second per megaparsec, the speed of recession per unit of distance. This value implied an age of the universe of roughly 13 to 14 billion years. The uncertainty was still significant, but the measurement was far more precise than anything achieved before. The cosmic microwave background, CMB, is the faint thermal radiation that fills all of space uniformly, left over from the early universe. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons to form neutral hydrogen atoms. Before that moment, the universe was opaque, filled with a dense hot plasma through which light could not travel freely. After that moment, the universe became transparent, and the light that had been trapped in the plasma was released, streaming outward in all directions. That released light has been traveling ever since, cooling as the universe expanded, its wavelengths stretching like a sound from a receding source. Today, it fills the sky at a temperature of just 2.725 Kelvin, barely above absolute zero, in the microwave part of the electromagnetic spectrum. It was detected accidentally in 1965 by Arno Penzias and Robert Wilson at Bell Telephone Laboratories, who were puzzled by a persistent hiss in their antenna and eventually realized they were hearing the echo of creation. The detailed structure of the CMB, the tiny variations in temperature across the sky, encodes an enormous amount of information about the early universe, its composition, its geometry, its expansion rate, and its age. Mapping that structure with precision became the goal of successive space missions. The Cosmic Background Explorer, (COBE), in the 1990s, the Wilkinson Microwave Anisotropy Probe, WMAP, in the 2000s, and the Planck satellite in the 2010s. The Planck mission, completed by the European Space Agency, produced the most precise measurements of the CMB structure ever made. Its results, published in 2013 and refined in subsequent years, yielded a value for the age of the universe of 13.799 plus or minus 0.021 billion years. This is an extraordinarily precise measurement. The uncertainty is less than 0.25%. It is, to date, our best estimate of when everything began. And so, the universe is approximately 13.8 billion years old. Now the question returns to the star. If the universe is 13.8 billion years old, and if HD 140283 is 14 to 16 billion years old, the paradox is explicit and unavoidable. Something must be wrong. Either the star's age estimate is too high, or the universe's age estimate is too low, or there is something about the physics involved that we do not yet fully understand. The search for the answer required new instruments, new techniques, and a level of patience and precision that speaks to something very particular about how science actually works, not in sudden leaps, but in the slow accumulation of better and better measurements, each one narrowing the uncertainty by a little. Part 5, Parallax and the Precise Distance. How do you know how far away a star is? This question underlies almost every other question in the story of the Methuselah star. Because the age estimate, the one that appeared to exceed the age of the universe, depends critically on knowing the star's true luminosity. And the star's true luminosity depends on knowing exactly how far away it is. Think of it this way. If you see a light in the distance, you might judge it to be quite faint, and conclude that the source itself is a dim one. But if you then walk toward it and find that it is far brighter than you expected, you realize your distance estimate was wrong. The apparent faintness was an artifact of distance, not a property of the source. The same logic applies to stars. A star may appear faint in our sky either because it is genuinely dim, or because it is genuinely far away. To separate these two effects and find the true, intrinsic brightness of the star, you need an accurate distance measurement. The most direct method of measuring stellar distances is called parallax, a technique so old and so fundamental that it has been used, in principle, since ancient times. Hold your thumb up in front of your face. Close your left eye and note where your thumb appears against the background. Now open your left eye and close your right eye. Your thumb appears to shift against the background. The amount of that shift depends on the distance to your thumb. The closer your thumb, the larger the shift. This is parallax. For nearby stars, the same effect can be measured using the Earth's orbit around the Sun as the baseline. As the Earth moves from one side of its orbit to the other, a distance of about 300 million kilometers, nearby stars appear to shift very slightly against the background of much more distant stars. The amount of that shift, the parallax angle, can be measured, and from it the distance to the star can be calculated with straightforward geometry. The unit of distance most commonly used by astronomers, the parsec, is defined by this technique. 1 parsec is the distance at which a star shows a parallax of 1 arcsecond, 1/3600th of a degree. In physical terms, 1 parsec is about 3.26 light-years, or approximately 30 trillion kilometers. HD 140,283 is approximately 58 parsecs from Earth, about 190 light-years. At that distance, the parallax angle is tiny, a fraction of a millisecond. Measuring it accurately requires instruments of extraordinary precision. For most of the 20th century, stellar parallax measurements were made from the ground, using large telescopes and precise measuring equipment. The best ground-based measurements could achieve accuracies of a few tenths of a millisecond for nearby stars. For HD 140283, that was not quite good enough to pin down the distance, and the distance, with the precision needed to resolve the age paradox. The breakthrough came from space. In 1989, the European Space Agency launched a satellite called Hipparcos, named both for the ancient Greek astronomer Hipparchus and as an acronym for High Precision Parallax Collecting Satellite. Its mission was to measure the parallax, and therefore the distance, of over 100,000 stars with unprecedented precision. Hipparcos operated for about 3.5 years, measuring the positions of stars with an accuracy of about 1 millisecond. For relatively nearby stars like HD 140283, this was a significant improvement over ground-based measurements. The Hipparcos data, released in 1997, gave astronomers a much better distance estimate for HD 140283, and with it a better estimate of the star's intrinsic luminosity. The revised distance from Hipparcos made HD 140283 somewhat farther away than some earlier estimates had suggested. And a star that is farther away, but appears equally bright in the sky, must be intrinsically more luminous. And a star that is intrinsically more luminous is, in stellar evolution models, further along in its life, meaning it is older. So in one sense, the Hipparcos data made the problem worse. It pushed the estimated age of HD 140283 upward, rather than resolving the tension with the age of the universe. The next step in the parallax story came 2 decades later, from a successor mission. The Hubble Space Telescope, despite being designed primarily for imaging rather than astrometry, was used in the early 2000s with a technique called fine guidance sensor astrometry to measure the parallax of HD 140283 with even greater precision. The result, published by Howard Bond and colleagues in 2013, was a parallax measurement with an uncertainty of only about 40 microarcseconds, extraordinarily precise, one of the most accurate parallax measurements ever made of any star. And with that precise distance in hand, the team recalculated the star's luminosity, its position in the HR diagram, and its age. The result, they found an age of 14.46 plus or minus 0.8 billion years. The central value was still above 13.8 billion years, the accepted age of the universe. But the uncertainty was large enough that the lower end of the age range, about 13.66 billion years, just barely overlapped with the age of the universe. The paradox was not fully resolved, but it had narrowed significantly. What had looked like a difference of 1 to 2 billion years, comfortably outside any reasonable error range, had become a potential overlap within the error bars. The impossible might, after all, be possible. But the story was not finished. Because the age estimate depends not only on the distance to the star, but also on the models of stellar evolution used to interpret the distance and luminosity. And those models, too, were being refined. Part 6. The physics inside a star. What happens inside a star that tells us how old it is? A star is not a simple object. From the outside, it looks like a smooth, glowing sphere, a point of light in the sky. But inside, it is an arena of staggering physical complexity. Nuclear reactions, fluid dynamics, radiation transport, magnetic fields, acoustic waves, all operating simultaneously, over timescales ranging from seconds to billions of years. The age of a star like HD 140283 is read not from its surface directly, but from its position in the HR diagram, its temperature and its luminosity, interpreted through models that simulate its interior physics. And those models, no matter how carefully constructed, depend on a number of physical parameters that are not perfectly known. One of the most important of these is the rate of the nuclear reactions that power the star. The energy of our Sun, and of most main sequence stars, comes primarily from the proton-proton chain, a series of reactions that converts hydrogen nuclei into helium-4, releasing energy in the process. The rate at which these reactions proceed determines how quickly the star consumes its hydrogen fuel, and therefore how quickly it ages. The precise rates of nuclear reactions in stellar interiors are measured in the laboratory through experiments in nuclear physics, but these experiments are difficult. The reactions that matter in stars occur at temperatures of tens of millions of degrees, and the cross-sections, the quantum mechanical probabilities of the reactions, are sometimes enormously small and difficult to measure at energies relevant to stellar interiors. Experiments in underground laboratories, shielded from cosmic ray interference, have steadily improved these measurements over the decades, and each improvement feeds back into the stellar models. Another critical parameter is the opacity of stellar material, how easily radiation travels from the core of the star to the surface. In the interior of a star, energy produced by nuclear reactions in the core makes its way outward primarily as radiation, photons bouncing and scattering through the dense stellar plasma. The opacity determines how quickly this energy diffuses outward, and therefore how the temperature gradient inside the star behaves. Opacity depends on the composition of the stellar material, how much hydrogen, helium, and heavier elements are present, and how they absorb and scatter radiation at different frequencies. For an old, metal-poor star like HD 140283, the composition is relatively simple, mostly hydrogen and helium, which actually makes the opacity calculation somewhat easier. But the physics is still complex, and improvements in atomic data and quantum mechanical calculations have been progressively refining these numbers. A third important parameter is what astrophysicists call convective overshooting, the degree to which convection in the stellar interior mixes material between different layers. In some regions of a star, energy is transported by the bulk movement of gas, hot, less dense gas rising while cooler, denser gas sinks, in a pattern analogous to what you see in a pot of water heated on a stove. This is convection. The boundaries between convective and non-convective zones in a star, the edges of the convective cells, are not perfectly sharp. Material can overshoot the formal boundary and mix into the adjacent layer. The degree to which this happens affects the star's internal composition profile, and therefore its evolution over time. Different values of this parameter produce different evolutionary tracks in the HR diagram, and therefore different inferred ages. All of these parameters introduce uncertainties into the stellar age estimates. But they do not all work in the same direction. Some tend to make the star appear older, others make it appear younger. The challenge for stellar physicists is to reduce each of these uncertainties as much as possible, and to understand clearly how they affect the final age estimate. Over the first 2 decades of the 21st century, a significant amount of work was devoted specifically to improving the modeling of old, metal-poor stars like HD 140283. New atomic physics calculations improved opacity data. Better measurements of nuclear reaction rates came from underground laboratories, particularly the Luna experiment deep under the Gran Sasso mountain in Italy. More sophisticated three-dimensional models of stellar convection were developed, replacing the simpler one-dimensional approximations used in earlier work. The effect of all these improvements was, gradually, to lower the central value of the estimated age for HD 140283. Not by a dramatic amount, the star is undeniably very old, the oldest known free-floating star in the Milky Way's vicinity. But the highest estimates of 16 billion years gave way to more carefully constrained estimates closer to 13 or 14 billion years. The current best estimate, as of the most recent careful analyses, suggests an age for HD 140283 of approximately 13.7 plus or minus 0.7 billion years. The central value is just barely below the age of the universe. The lower end of the range, about 13.0 billion years, is comfortably consistent with a universe 13.8 billion years old. The star is not impossibly ancient. It is simply genuinely, staggeringly ancient, born within the first 100 million years or so after the Big Bang itself. It is worth pausing to let that sink in. 100 million years after the Big Bang. The universe is young, barely a glimmer of its current age. The first generation of massive stars has only recently begun to form, lived their brief intense lives, and scattered the first traces of heavier elements into space. And in the debris of that first generation, in the first faint pollution of the primordial hydrogen and helium, HD 140283 was born. It has been burning, very slowly, ever since. For longer than the Earth has existed. For longer than the Sun has existed. For nearly as long as the universe has allowed anything to exist. Part 7, The First Stars and the Cosmic Dark Ages. What were the first stars like, and could they have given birth to HD 140283? To understand where HD 140283 came from, we need to understand the universe in which it was born, a universe so different from the one we inhabit today that it is almost unrecognizable. The Big Bang occurred approximately 13.8 billion years ago. In the first fraction of a second, the universe was a hot, dense plasma of elementary particles. Over the next few 100,000 years, it expanded and cooled, and the first nuclei formed, hydrogen, helium, and trace amounts of lithium. These are the primordial elements, the raw material from which the first stars would eventually be made. After the release of the cosmic microwave background, about 380,000 years after the Big Bang, the universe entered a period that cosmologists call the Cosmic Dark Ages. The universe was filled with neutral hydrogen gas, transparent but empty of light sources. There were no stars, no galaxies, no blazing points of light. Just an expanding, cooling, darkening fog of gas. But the gas was not perfectly uniform. Tiny density fluctuations, Quantum ripples imprinted in the fabric of space during the first moments after the Big Bang and amplified by the subsequent expansion, meant that some regions of the universe were very slightly denser than others. Gravity, patient and relentless, began to amplify these fluctuations. Over millions of years, denser regions drew in surrounding gas, and eventually, perhaps 200 to 400 million years after the Big Bang, the first stars began to form. These first stars, known as population 3 stars in astronomical nomenclature, were different from any star we can observe today. They formed from primordial gas containing only hydrogen, helium, and trace lithium. No carbon. No oxygen. No nitrogen. No iron. Nothing heavier. The absence of heavy elements affected the way gas cooled as it collapsed to form stars. Heavier elements are efficient radiators. They help gas shed heat as it compresses. Without them, primordial gas could not cool as efficiently, and star formation proceeded differently. The best theoretical models suggest that population 3 stars were enormous, perhaps tens or even hundreds of times the mass of our Sun. And massive stars burn hot and fast. They may have lived for only 1 million years or so before exploding as the most powerful supernovas the universe has ever produced. Those explosions seeded the surrounding gas with the products of nuclear fusion, carbon, oxygen, nitrogen, iron, and other heavy elements. This first wave of chemical enrichment was the beginning of a process that would continue for billions of years, each generation of stars making heavier elements and scattering them back into space, building up the chemical complexity of the universe incrementally. HD 140283 was born in the second generation, or perhaps the third, of this process. It formed from gas that had been very lightly enriched by the deaths of population 3 stars. Lightly is the key word. The star contains only about 1/250th as much iron as our Sun, a metallicity of about equals -2.4, in the logarithmic scale astronomers use. This is one of the lowest iron abundances observed in any star. It places HD 140283 squarely in what astronomers call population 2, the old, metal-poor stars that formed in the early universe from gas barely touched by the chemical legacy of the first generation. What was the universe like when HD 140283 was born? The answer is genuinely staggering to contemplate. The universe was perhaps 100 to 500 million years old. The first galaxies were just beginning to assemble, primitive, irregular concentrations of stars and gas held together by dark matter halos. The structures of the modern universe, the vast web of galaxy clusters and filaments and voids, were only just beginning to emerge from the gentle tidal forces of the early cosmos. HD 140283 was born somewhere in this chaotic, forming universe, perhaps in what is now a dwarf galaxy that was later consumed by the early Milky Way, perhaps in a dense cluster of old stars that has since dispersed. It has been moving through the galaxy ever since, following an orbit that takes it high above and below the galactic plane, a characteristic of old population 2 stars, which tend to have more eccentric, inclined orbits than younger stars born in the flat disk of the galaxy. Astronomers have studied HD 140283's orbit carefully. It moves through the galaxy on a highly elliptical path that carries it far from the galactic center, high into the halo of the Milky Way, and then back down. It is, in a sense, a visitor to the solar neighborhood, passing through on its long, slow circuit of the galaxy. We happen to be alive during the brief period when it comes relatively close to our part of space. In its lifetime, nearly 14 billion years, the star has witnessed the formation and evolution of everything we know. The Milky Way galaxy was assembled around it. Our Sun formed, some 5 billion years ago, from a cloud of gas enriched by 10 billion years of previous generations of stars. The Earth formed. Life emerged. Dinosaurs lived and died. Humans arose and looked up at the sky. And HD 140283 was already old when our Sun was born. Part 8, The Hubble Tension and New Complications. Is the universe itself perhaps older than we thought? Just when the paradox of HD 140283 seemed to be resolving, just when the star's estimated age had been carefully revised downward and the universe's age had been carefully pinned down by the Planck satellite, a new and unexpected complication arose. It came not from the study of old stars, but from an entirely different corner of cosmology. And it reopened a question that many scientists thought had been settled: what exactly is the Hubble constant? The story begins in the late 2010s. By that time, there were two highly precise, independent methods of measuring the Hubble constant, and they were in clear disagreement. The first method was the one we have already discussed, the cosmic microwave background, as measured by the Planck satellite. This is called an early universe measurement. It is based on observations of the universe as it was when it was less than 400,000 years old, and it uses a cosmological model to extrapolate from those early conditions to the current expansion rate. The Planck measurement gives h is almost equal to 67.4 plus or minus 0.5 kilometers per second per mpc. The second method is the cosmic distance ladder, the method used by the Hubble Space Telescope Key project and its successors. This is a late universe measurement, based on direct observations of the current universe. It uses Cepheid variable stars to calibrate distances to nearby galaxies, and then uses those galaxies to calibrate the distances to more distant ones, eventually reaching the regime where Hubble's law applies and the expansion rate can be directly measured. The most recent careful calibrations, using the Hubble Space Telescope and led by Nobel laureate Adam Rees, give h is almost equal to 73 plus or minus 1 km per second per mpc. These two values differ by about 8%. In itself, that might not sound alarming. But the precision of each measurement is now high enough that the difference cannot be explained by random measurement error alone. The probability that the two measurements agree, given their stated uncertainties, is extremely low, less than 1 in a million, in some analyses. This discrepancy is now known as the Hubble tension, and it is regarded as one of the most significant unsolved problems in modern cosmology. The Hubble tension matters for the story of HD 140283 in a specific way. If the higher value of the Hubble constant, 73 km per second per mpc, is correct, then the universe is expanding faster than the Planck measurement suggests. And a universe expanding faster is a younger universe. The age implied by h equals 73 is closer to 12.5 to 13 billion years, rather than 13.8 billion. A younger universe makes the star paradox worse, not better. If the universe is only 12.5 billion years old, and the star is 13.7 billion years old, the contradiction is back, with a vengeance. But if the lower value, h equals 67.4, is correct, the universe is 13.8 billion years old, and the star's age is consistent with this, if barely. So the Hubble tension is not just an abstract cosmological curiosity. Its resolution, whichever way it falls, will have direct implications for whether the Methuselah star remains a paradox or becomes merely a witness to the universe's earliest hours. The community of cosmologists has proposed many possible resolutions to the Hubble tension. Some involve refinements to the standard cosmological model, new forms of dark energy, or new physics in the early universe. Some involve the possibility of systematic errors in one or both measurements, subtle biases in the calibration of the distance ladder, or subtle effects in the CMB analysis. None of the proposed solutions has yet achieved consensus. The James Webb Space Telescope, launched in December 2021, has begun to weigh in on this debate. Its extraordinary sensitivity and resolution allow it to measure Cepheid variable stars in more distant galaxies than the Hubble Space Telescope could reach, providing new calibration points for the distance ladder. Early results from Webb have tended to support the higher value of the Hubble constant, suggesting that the tension is real and not merely an artifact of measurement bias in the Cepheid calibration. If the high Hubble constant is correct, and the universe is genuinely younger than 13.8 billion years, then the Methuselah star paradox is not fully resolved. It remains a live problem, demanding either a revised understanding of stellar evolution or new physics in the early universe. Perhaps, some theorists have suggested, there is new physics in the era before the CMB, physics that made the universe expand faster early on, reducing the CMB inferred age without affecting the late universe observations. This has been called the early dark energy hypothesis, a brief period of accelerated expansion in the early universe, driven by a form of dark energy that has since diluted away. Other theorists have proposed that the Hubble constant itself is not constant, that the expansion rate of the universe varies from place to place in ways that would affect local versus global measurements. This is deeply unconventional physics, running against the principle that the universe is homogeneous on large scales, but it has been explored seriously. The simple truth, as of now, is that the Hubble tension remains unresolved. And until it is resolved, the age of the universe remains uncertain enough that the Methuselah star sits in an ambiguous position, consistent with the universe's age under some interpretations, potentially paradoxical under others. And that ambiguity, if you sit with it gently, is not a cause for anxiety. It is a sign that cosmology is alive. It is a sign that the universe is still showing us things we do not understand. It is an invitation to keep measuring, keep modeling, keep questioning. Part 9: The Human Story of Discovery. Who were the people behind this long investigation, and what drove them? Science, in the popular imagination, often appears as a series of dramatic revelations, moments when a single brilliant mind achieves a sudden breakthrough that transforms everything. The reality of scientific practice is usually quite different. It is gradual, collaborative, unglamorous, and deeply dependent on the accumulation of careful work by many people over long periods of time. The story of HD 140283 is a perfect illustration of this reality. No single person discovered its paradoxical age. No single paper contained the key breakthrough. The story spans more than a century of observational work, theoretical development, and technological improvement, carried out by hundreds of astronomers across dozens of institutions on several continents. The star first appeared in the Henry Draper Catalog, that massive inventory of stellar spectra compiled at Harvard in the early 20th century. Number 140283 in that catalog, it was identified by its position in the sky and the characteristics of its spectrum: metal poor, old, and early type subgiant. It attracted the attention of researchers working on the ages and compositions of old stars, who recognized it as a particularly interesting specimen. One of the scientists who did sustained work on this star was George Preston, an astronomer at the Carnegie Observatories in Pasadena, California. Preston spent much of his career studying metal-poor stars, understanding their kinematics, how they move through the galaxy, and their chemical compositions. His work helped establish HD 140283 as one of the most metal-poor, and therefore potentially oldest, known subgiant stars. Other crucial contributions came from Pierre Demarque at Yale University, a pioneer in the theory of stellar evolution and the calculation of stellar isochrones. Demarque's group developed some of the most widely used stellar evolution models of the 20th century, and his work was directly applied to constraining the ages of old metal-poor stars like HD 140283. The Hipparcos satellite data, which transformed the distance measurement, was the product of an enormous European team effort over many years: satellite engineers, instrument developers, data analysts, and the scientists who designed and executed the observational program. The release of the Hipparcos catalog in 1997 opened a new era in precision astrometry. The Hubble Space Telescope parallax measurement, published in 2013, was led by Howard Bond of Pennsylvania State University, working with colleagues at STSCI, the Space Telescope Science Institute in Baltimore, Maryland. Bond had spent decades studying old stars and stellar populations, and the HD 140283 measurement was a culmination of a long program of careful astrometric work using the fine guidance sensors of the Hubble Space Telescope. What drove these scientists? The simple pleasure of knowing. There is something deeply human about wanting to understand the age of the oldest things, whether it is geologists reading the rock record, archaeologists dating ancient artifacts, or astronomers trying to date the oldest stars. We are a species that wants to know where it came from and how long things have been. There is also a practical scientific motivation. The ages of the oldest stars provide a lower bound on the age of the universe. The universe cannot be younger than the oldest things in it. Historically, before the CMB age measurements became available, old star ages were one of the primary constraints on cosmological models. Getting those ages right mattered not just for understanding individual stars but for understanding the universe as a whole. But the questions they have been pursuing are among the deepest questions anyone has ever asked. How old is the oldest star? How old is the universe? Are these numbers consistent? Do they tell a coherent story about how everything began? There is a particular kind of scientist, patient, meticulous, driven by a love of precision, who is drawn to problems like this one. Not problems of drama or catastrophe, but problems of measurement, questions that can only be answered by making numbers more and more exact, by reducing uncertainties fraction by fraction over years and decades. These are the quiet heroes of this story. Not people who made a single dramatic discovery, but people who spent careers making measurements slightly more precise, models slightly more accurate, instruments slightly more sensitive. And in doing so, they brought us closer to understanding something genuinely remarkable about the nature of time. Part 10, What HD 140283 is made of, a cosmic chemical story. What can the chemistry of an ancient star tell us about the very beginning? Every element in HD 140283, every atom of hydrogen, helium, carbon, oxygen, and iron, has a story. Not a metaphorical story, but a literal physical history, a record of where that atom was made, in what kind of nuclear furnace, at what temperature and pressure, and how it came to be incorporated into the star. Most of what HD 140283 is made of, roughly 75% by mass, is hydrogen. Simple hydrogen, a single proton, the most abundant nucleus in the universe. This hydrogen was made in the Big Bang itself, in the first minutes after the beginning, when temperatures were high enough for protons to form but not high enough for any complex nuclear structure to survive. It is 13.8 billion years old as anything in the universe. About 25% is helium. Again, mostly Big Bang helium, the helium-4 nuclei that formed in the first 3 minutes of the universe's existence, during a brief window of nuclear fusion that cosmologists call Big Bang nucleosynthesis. The ratio of hydrogen to helium in the universe, very close to 3:1 by mass, is one of the key predictions of Big Bang theory, and it is confirmed by measurements of old stars like HD 140283 and of intergalactic gas clouds. But HD 140283 is not made only of hydrogen and helium. It contains trace amounts of heavier elements, measurable, though tiny compared to what our Sun contains. And these heavy elements are not from the Big Bang. They were made in stars. Among the elements detectable in HD 140,283 spectrum are carbon, nitrogen, oxygen, magnesium, calcium, titanium, and iron. All of these were made in the interiors of stars, the first generation of stars that formed from the pure primordial hydrogen and helium cloud. The particular pattern of abundances, which elements are present and in what ratios, is a direct fingerprint of the nuclear processes that created them. Different elements are produced in different ways, under different conditions, and the ratio of their abundances in HD 140,283's atmosphere encodes information about the stars that enriched the gas cloud from which it formed. One striking feature of HD 140,283's chemistry is its ratio of alpha elements, oxygen, magnesium, silicon, calcium, and titanium, to iron. In the Sun and in stars of similar age to the Sun, this ratio is close to 1. The abundances of alpha elements and iron are roughly in balance, reflecting the long history of contributions from both core-collapse supernovas and type Ia supernovas over many billions of years. But in HD 140283, the alpha elements are enhanced relative to iron. The ratio of, say, magnesium to iron is several times higher than in the Sun. This is called alpha element enhancement, and it is a common signature of very old stars. Why does this happen? Core-collapse supernovas, the deaths of massive stars, produce large quantities of alpha elements but relatively little iron. They happen quickly, because massive stars live short lives. Type Ia supernovas, the thermonuclear explosions of white dwarf stars in binary systems, produce large quantities of iron, but they take longer to occur, because the white dwarf must accumulate mass from a companion star over a period of time, typically hundreds of millions of years. So in the very early universe, when HD 140283 was forming, the only supernovas that had occurred were core collapse events, the deaths of the first generation of massive stars. The Type Ia supernovas had not yet had time to contribute. The gas that formed HD 140283 was enriched primarily by core collapse supernovas, giving it its characteristic alpha-enhanced chemistry. As the universe aged and Type Ia supernovas began to contribute, later generations of stars, including our Sun, formed from gas that was more balanced in its alpha-to-iron ratio. The chemistry of a star's atmosphere is thus a record of the chemical history of the universe at the time and place of its formation. Reading this chemical record has become a subfield of astronomy in its own right, called chemical evolution or chemodynamics. By mapping the compositions of thousands of old stars across the galaxy, astronomers are piecing together the history of how the Milky Way assembled itself, which parts formed early, which formed late, and how material was mixed and exchanged between different regions. HD 140283, in this context, is one of the key calibration points, a star whose composition is so extreme, so metal-poor and alpha-enhanced, that it anchors the very earliest end of the chemical evolution timeline. It is a record of what the universe looked like in its infancy, preserved in the atmosphere of a star that has been burning slowly and steadily ever since. There is something deeply moving, if you let yourself feel it, about the idea that a star carries within its atmosphere the chemical legacy of the universe's first explosions. That the iron and magnesium in HD 140283 were forged in the cores of stars that no longer exist, stars that burned brilliantly for 1,000,000 years and then perished, scattering their contents into the void, and that this material was gathered up again by gravity, hundreds of millions of years later, to form a new star that has endured ever since. The universe recycles everything. Nothing is lost. The atoms that were hydrogen 13 billion years ago are still hydrogen today, or have been fused into helium or heavier elements and scattered into space and gathered into new stars and planets. They have been on a long journey. And some of those atoms, a tiny fraction, are in a star called HD 140283, 190 light-years from here. And we have learned to read the story they carry. Part 11, What the Methuselah Star Teaches Us About Time. What does it mean for the universe that such an old star exists? There is a way of thinking about the universe that treats it as a kind of clock, an enormous, self-contained system in which time began at a particular moment and has been running ever since. In this view, the age of the universe is not just an astronomical number. It is the total span of time within which all physical processes have occurred. It is the depth of the past. HD 140283 is a marker in that depth. It formed approximately 13.6 to 13.7 billion years ago, perhaps 100 million years after the Big Bang, perhaps as much as 500 million years after, depending on the exact age estimate and the exact age of the universe. Either way, it formed very close to the beginning. It is one of the earliest surviving relics of the universe's first chapter. Consider what it means to say that a star has been burning for nearly 14 billion years. Our Sun is about 4.6 billion years old. The entire history of Earth, from the formation of the first oceans, through the emergence of single-celled life, through the Cambrian explosion and the age of dinosaurs and the rise of mammals and the evolution of humans and the entirety of human civilization, all of that is contained within the last 4.6 billion years. HD 140283 was already 9 billion years old when our Sun was born. It had been burning for 9 billion years before our planet existed. In all that time, it has changed slowly. It is a low-mass star, about 80% of the Sun's mass, which means it burns slowly, frugally, on a timescale that seems almost geological. It has spent most of its existence on the main sequence, fusing hydrogen in its core at a rate calibrated to last for many billions of years. Only in the last few 100 million years has it begun to evolve off the main sequence, its core hydrogen now largely exhausted, its outer layers gradually expanding as it becomes a subgiant, the stage just before full red gianthood. In a few billion more years, perhaps 2 or 3 billion, HD 140283 will swell dramatically, becoming a true red giant, its outer atmosphere expanding to perhaps 100 times its current diameter. It will then shed those outer layers as a planetary nebula, a beautiful shell of glowing gas expanding into space, leaving behind a dense, hot white dwarf about the size of Earth. The white dwarf will then cool over trillions of years, fading from white to yellow to orange to red to black, a cold dark cinder drifting through the galaxy until the end of cosmological time. In the meantime, it burns. Slowly, quietly, at a temperature slightly cooler than our Sun, its surface a deep yellow-orange, its light traveling 190 years through space before it reaches any instrument or eye that could appreciate it. The existence of a star this old has implications that extend far beyond the individual object. It tells us something important about the early universe, about how quickly the first structures formed, how efficiently the first star-forming clouds assembled themselves from primordial gas, and what conditions prevailed in the galaxy before any of the structures we observe today had come to exist. It tells us, specifically, that the universe was capable of forming long-lived stars, stars that would persist for nearly the full age of the universe, within a few 100 million years of its beginning. This places constraints on the efficiency of the first star formation, on the mass distribution of population 3 stars, and on the speed with which chemical enrichment occurred. HD 140283 is also a member of a broader class of stars, the so-called extremely metal-poor and ultra-metal-poor stars, that are being discovered and characterized in increasing numbers through large spectroscopic surveys like GALA, Apogee, and the HK survey. Each of these stars is a probe of the earliest universe, a messenger from a time when the galaxy was still forming and the chemical elements we are made of were just beginning to be produced. Some of these stars are even more metal-poor than HD 140283. A star called He 0107 to 5240, discovered in 2002, has an iron abundance more than 200,000 times lower than the Sun's. Another, He 1327 to 2326, is even more extreme. These hypermetal-poor stars may actually be members of the second or third generation after the first stars, survivors from a time so remote that the universe had barely begun to make anything heavier than helium. The search for population 3 stars, first generation, zero metallicity, continues. No confirmed example has yet been found in the Milky Way, and this is expected. First-generation stars were massive, short-lived, and would have died billions of years ago. But their existence is inferred from the chemical signatures they left in the next generation, and the search for stars with extremely peculiar abundance patterns, signatures of pollution by individual first-generation supernova explosions, continues to yield fascinating results. HD 140283 stands near the beginning of all this history, a solitary, ancient, unassuming point of light in the direction of Libra, carrying within itself the chemical legacy of events so ancient that no human being could fully imagine them. And yet here we are, imagining them. That is perhaps the most remarkable thing of all, that the human mind, in the brief moment of its existence, has found a way to look at the light of a star and read in it the history of the universe's first days. Part 12, What Remains Unknown, and Why That Is Beautiful. What do we still not understand, and what does that open up? Science is sometimes imagined as a process of closing doors, answering questions, resolving mysteries, reducing the unknown. In the popular imagination, a problem solved is a mystery concluded, a chapter finished. But anyone who has spent time in science knows that the reality is different. Every answered question opens two new ones. Every measurement made with greater precision reveals new discrepancies. Every mystery resolved uncovers a deeper mystery beneath it. The story of HD 140283 is not a closed story. It is a story in progress. Pause. The Hubble tension remains unresolved. The age of the universe itself, 13.8 billion years, is a best estimate, not a final answer. And the age of HD 140283, currently estimated at somewhere between 13.0 and 14.5 billion years, depending on which models and measurements you use, carries uncertainties that are themselves uncertain. That is not a paradox. It is an honest accounting of what we know and what we do not. Let us take stock of what remains genuinely open. The first open question concerns the star's distance. The Hubble Space Telescope parallax measurement published by Howard Bond's team in 2013 was the most precise available at the time. But the Gaia satellite, launched by the European Space Agency in 2013, has since produced a new generation of parallax measurements for over 1 billion stars, with precisions that dwarf even the best previous work. Gaia's measurement of HD 140283 gives a distance that is slightly different from the Hubble measurement, by a small but potentially significant amount. The Gaia data release in 2018 and subsequent data releases have provided a parallax for HD 140283 of approximately 17.15 plus or minus 0.14 milliarcseconds, implying a distance of about 58 parsecs. This is consistent with the Hubble measurement, but the uncertainty is smaller. And a smaller uncertainty means that the constraints on the star's age from the distance measurement are tighter. The star cannot hide its luminosity behind a large error bar. The number it presents to us is more precisely known. With the Gaia distance, and the best current stellar models, the star's age is estimated at approximately 13.5 to 14.0 billion years, with an uncertainty of roughly plus or minus 0.7 billion years. The central value is still slightly above the Planck age of the universe, but well within the combined error bars. It is not a contradiction. It is a near miss, an ancient star, formed very close to the earliest possible time. But the Gaia data also opens new questions. Gaia has measured the positions, parallaxes, and proper motions, the movements across the sky, of more than 1 billion stars with exquisite precision. From these measurements, astronomers are able to reconstruct the orbits of stars in the Milky Way with a level of detail never before possible. The orbit of HD 140283, as reconstructed from Gaia data, is highly elliptical, a long, looping path that carries the star far from the galactic plane and deep into the galactic halo. This confirms what had long been suspected: the star is a halo star, born in the earliest days of the Milky Way's assembly, moving through the galaxy on an orbit that has barely changed in nearly 14 billion years. Where was the star born? That is another open question. The most likely scenario, based on its chemical composition and orbital properties, is that it formed in one of the earliest protogalactic fragments that eventually merged to form the Milky Way, perhaps a small dwarf galaxy, long since consumed and dissolved, whose stars now populate the galactic halo. But the precise birthplace of HD 140283 is unknown, and may remain unknown. The Gaia survey has identified several ancient dissolved stellar streams, the remains of ancient star clusters and dwarf galaxies stretched into ribbons by the tidal forces of the Milky Way. Some of these streams may be from the very earliest epoch of galaxy assembly. It is possible that HD 140283 is a member of one of these streams, a fragment of a primordial structure that is otherwise invisible. But proving this requires more data, more careful analysis. A second area of ongoing uncertainty concerns the stellar models themselves. Even with all the improvements made over the past 2 decades, the models used to estimate stellar ages are still imperfect. They rely on simplifications, on treating the star's interior as one-dimensional, spherically symmetric, time-averaged, that are necessary for practical computation but may introduce systematic biases. 3-dimensional simulations of stellar interiors have been making rapid progress in recent years. These simulations, running on supercomputers, solving the full equations of fluid dynamics, radiation transport, and nuclear physics in 3 dimensions, reveal complex mixing patterns and convective motions that simpler models cannot capture. The results suggest that convective overshooting and other mixing processes may be somewhat different from what one-dimensional models assume, and this could affect the estimated ages of old stars. Resolving these questions requires both better computational models and better observational data. Asteroseismology, the study of oscillations in stellar interiors, analogous to seismology on Earth, provides one route. Stars oscillate in a variety of modes, and the frequencies of these oscillations carry information about the star's internal structure, its density profile, temperature gradient, and composition. By measuring these oscillations precisely, astronomers can test and constrain stellar models with a detail that surface observations alone cannot provide. HD 140283 is close enough and bright enough that its oscillations may be detectable with dedicated space-based observations. The ESA Plato mission, planned for launch in the late 2020s, is designed partly to do asteroseismology of bright nearby stars with high precision. If it can detect the oscillations of HD 140283, it will provide an independent constraint on the star's internal structure and age, a completely different line of evidence that can be compared with the isochron estimates. There is also the open question of composition. The iron abundance of HD 140283, its metallicity, is measured from the absorption lines in its spectrum, and the precision of this measurement has been steadily improving. But there are subtleties. The temperature structure of the star's atmosphere affects the depth and shape of spectral lines in ways that are modeled through what astrophysicists call model atmospheres. The accuracy of these model atmospheres, how well they capture the actual physics of the star's photosphere, affects the derived abundances, and therefore the age estimates that depend on composition. Recent work using three-dimensional model atmospheres, again, more realistic than the simpler one-dimensional models traditionally used, suggests that the derived abundances of old, metal-poor stars may shift slightly when 3D effects are taken into account. The direction and magnitude of these shifts are still being actively studied. None of these open questions change the fundamental conclusion: HD 140283 is genuinely, extraordinarily ancient. It is among the oldest known stars in the observable universe. Whatever the final, most precise estimate of its age turns out to be, 13.5 billion years, 13.8 billion years, perhaps as high as 14.2 billion years within the remaining uncertainty, it was born very close to the beginning of everything. But the open questions matter, because they are pointing us toward a deeper understanding of stellar physics, galactic history, and cosmology. Each improvement in precision, each reduction in uncertainty, is not just about pinning down one star's age. It is about building a more complete and coherent picture of how the universe evolved from its beginning to the present day. And there is something else worth saying about what remains unknown. The Hubble tension, the discrepancy between the early universe and late universe measurements of the expansion rate, may be telling us something profound about the nature of the universe. If the tension is real, and not a measurement artifact, it could point to physics beyond the standard cosmological model, new forms of dark energy, new interactions in the early universe, or something even more surprising. Some theorists have proposed that the tension points to a form of dark energy that varied in strength early in the universe's history, a brief period of enhanced energy density that would have changed the expansion rate in ways that current models do not account for. If such early dark energy exists, it would slightly change the inferred age of the universe from the CMB data. Interestingly, it would tend to make the universe slightly younger, potentially worsening the tension with old stars like HD 140283, or to redistribute the uncertainty in ways that require new calibration. Others have proposed modifications to gravity on cosmological scales, or the existence of additional species of neutrinos, or subtle systematic effects in the calibration of standard candles. The debate is ongoing, active, and unresolved. What is remarkable is that a single ancient star, 190 light-years away, barely visible to the naked eye even from a dark sky, unremarkable in its physical appearance, sits at the intersection of all these questions. Its age constrains the expansion history of the universe. Its composition records the chemistry of the universe's first stellar populations. Its orbit traces the assembly history of the Milky Way. It is a single data point that links stellar physics, cosmology, and galactic archaeology in a way that makes it uniquely informative. The universe has a way of hiding its deepest lessons in unexpected places. The oldest star known is not a dramatic object. It does not explode or collapse. It does not pulse or flare. It is simply there, burning quietly in the direction of Libra, tracing its ancient orbit through the halo of the galaxy, outlasting generation after generation of everything around it. That is perhaps the deepest lesson of the Methuselah star. Not the specific number, 13.7 billion years, or whatever the next refinement brings, but the process. The long, patient, collaborative process of measuring the universe more precisely than before. Of sitting with an impossible number and not discarding it, but investigating it. Of following the evidence wherever it leads, even when it leads somewhere uncomfortable. The star does not know we are watching it. It does not know that we have spread its light through spectrographs and measured its absorption lines and tracked its tiny movement across the sky with satellites of extraordinary precision. It simply burns. But we know. And in knowing, we have learned something about the age of the universe, the chemistry of its earliest moments, the physics of stellar interiors, and the history of the galaxy in which we live. We have learned all of this from one faint, ancient point of light. There are approximately 400 billion stars in the Milky Way. We have studied HD 140283, one of them, with more care and precision than almost any other. And the things it has taught us have reverberated through every branch of astrophysics. Imagine what the others might tell us, if we learned to listen as carefully to them. Closing meditation. The night sky outside is still there. Whether you can see it from where you are, or whether clouds have gathered, or whether the city's glow obscures the stars, they are there. Hundreds of billions of them in this galaxy alone. Trillions of galaxies beyond. A universe so large and so old that the numbers lose their meaning in any practical sense. And yet, somewhere in that darkness, at a distance of 190 light-years, a distance that sounds vast but is, cosmically speaking, barely a step, there is a small, ancient, orange-yellow star. It has been burning since very close to the beginning. It burned before our sun existed. It burned before the earth existed. It burned through all of geological time, through all of biological time, through all of human history. It is burning now, as you lie here. It will still be burning long after tonight. Long after every person alive today has lived their full life. The Methuselah star is in no hurry. It burns slowly, patiently, with a profligacy measured in billions of years. There is something deeply calming about that. About the existence of something so old and so steady. About the fact that the universe can produce something that outlasts everything we know, not through drama or force, but simply through the quiet persistence of nuclear fire, balanced against the pressure of its own gravity, burning on in the dark. The questions we have been sitting with tonight: how old is the universe? How old are the oldest stars? What do the measurements mean? What remains unknown? These are not questions you need to hold tightly tonight. You can let them settle gently, the way sediment settles to the bottom of still water. Let the mysteries remain open. Let the universe be as large and as ancient as it is. There is no need to resolve it tonight. There is only the dark, and your breath, and the distant light of stars older than anything you can touch or name. The Methuselah star has been burning for 13 billion years or more. It can burn for a few more hours while you sleep. Rest now. The universe is very old. You are very small. Both of these things are beautiful. Sleep well. If you're still awake, the universe is vast and full of wonder. Subscribe to Cosmos and Dreams for a new discovery every week. Sweet dreams.